Thank you very much, Arvin, and thank you for the invitation. It's a very enjoyable conference. I can understand now if someone goes to the coffee, we will all follow, so I will try to attract you here. There is still enough to like for the moment. So I would like to tell you about swarm robotics, which is a field that I have entered pretty recently. And so it's really ongoing work that has been performed with these students, and it's also a collaboration with Nicolas Bredesch, who is really the guy from robotics, and my long-standing collaborator, Eric Bertin, with Misaki Ozawa and Gerhard Jung in Grenoble. Okay, so today, what I want to discuss are essentially 2 points. One is this problem of swarm robotics and what roboticians themselves call the reality gap, which is essentially the fact that there is really a lot of work in robotics and swarm robotics where you design model of your robots and then you simulate them to see how they behave. And then when you implement the thing in the real world, well, it doesn't work. And it doesn't work by far. So that's what they call the reality gap. And this is really because there is a very strong importance of the design, the detailed design of the robot, which is one thing that I will discuss on a very, very simple case. And then I will move to evolutionary swarm robotics, where you implement social learning or collective learning in a swarm of robots. And I will try to show that we can try to describe this at large scale through some kind of hydrodynamics description. And then a swarm of robots becomes essentially a learning active liquid. Okay, so let's start with, so swarm robotics is essentially, for me, it's active matter. I will not define active matter. I like the one of this morning. I think it was very good. And so I will stick to it. And then robots means they have sensors and controllers. Controllers is really the minimal brain you can think of that taking the sensor will make some kind of action, some actuator. But they will not be really intelligent yet. So the actor at play is the Kilobot. The Kilobot was designed now 10 years ago. It's a very, very elementary robot where you have one light sensor, essentially 2 little vibration motors, 3 legs, 1 communication channel, and 1 simple processor. It's actually a controller, not really a processor. And it was used to perform this experiment where 1,000 kilobots, and hence their name, kilobots, was able to design a shape. But I want to insist here on the fact that there is not really any intelligence there except from the human being who designed the algorithm for them to do that. They are performing almost systematic action, and you could notice from the movie that they essentially move along the boundaries, and all of this is very planned. Okay. Also, you can see that this movie is pretty much accelerated because these kilobots are extremely slow. And that's why the first thing we did when we started to work with them was to design them an exoskeleton that is a 3D printed body that makes them walk a little bit faster than these poor kilobots. It's true that this kind of legs, you could imagine it's not super efficient. And so when we 3D print this body, we have a French kilobot that is going a bit faster. So once we have this, because otherwise we cannot run large-scale experiments, I will start by discussing really the most elementary task of swarm robotics, which is phototaxi. But it's phototaxi without gradient of light. You just have a light spot, and if you are in the dark, you are in the dark, you have no idea of the light, your sensor is on your head, and if you are in the light, well, then you are in the light, and that's it. Okay, so the goal is to aggregate in the light. And so you essentially do something really very simple. You program 2 dynamics inside each robot. The first dynamics, D0, is an exploration one. You program some kind of run and tumble with long and fast run with a typical velocity 1. And then you have an exploitation dynamics. I will really take the extreme case. The velocity is 0. That is, you stop in the light. And then you need a controller. And the controller will be, again, something very simple. You have 1 input, which is the light sensor, and 1 output, which is just a selection of the dynamics. So the goal is just to have the good threshold. You cannot make something simpler than that. Okay, so you do this, you run the experiment. So you have put the threshold at the right value, the design is not complicated, and you run your experiment, and then what you see is that it doesn't work. That is, after half an hour, you have a fraction of your robots that has more or less entered the light, but then after 2 hours and a half, you barely did better than that, and there are still many robots running outside. And the reason is that because they stop at the boundary, they build a wall to the others. And this is typically an example of reality gap. Because, of course, if you simulate point particles or robots that do not collide, this would not happen. So this is, but then what is more intriguing is that you can redo the experiment just changing a little bit the exoskeleton. I will come back to that in a minute. So you see, I just changed somehow the shape of the legs. And then in this case, in 2 hours and a half, you actually do better than that. You can quantify this. The difference is not very large, but you can also simulate this system for many more robots, and then you see that the difference becomes sharper. So it means that a little details about the legs actually matters on the global behavior of the crowd. And you could have things, okay, what I should do is to try to avoid collisions or to give them a very clever policy when they arrive at the boundary so that they should go by themselves inside. And actually, it's just a simple change of the legs that change the things. So this is connecting to what we heard this morning about morphological computing. It's just that by the shape, you behave differently. And there is a very famous examples where you have this extremely complicated hand where you have essentially many controllers for many simple linear sensors and actuators that you can contrast with this case where you have a single controller for just one scalar, which is the pressure, but acting on a strongly nonlinear and high-dimensional state space. And that's a matter of choice. And sometimes it's a good idea to do that. Sometimes it's a more clever idea to do that. Okay, so design really matters. Let's come back to our little guy and let's make this following experiment. So I take the kilobot and I wanted to solve this complicated task which consists in remaining at equilibrium, not falling from this table. Unfortunately for it, the table has only one point of contact, and so it's a swinging table. Okay, now you have to stay on that table. So we start with the kilobot. So we put it on this table, and well, the poor guy is doing really poorly. So well, we try by giving a little bit more chance, put it in closer to the center, but again, the guy really does perform very, very badly. We can repeat this experiment many times, and well, it will always be the same conclusion. Now we try a second time, and again, we change a little bit the morphology. And now what we see is that this guy is doing actually much, much better. And you can see that each time he's approaching the side, it avoids it, and it can stay like this for a long time. Eventually, it will fall down because there is still some stochasticity. Well, no, it didn't. Okay, so again, what did we change? The legs. And we changed the legs exactly in the same way as we changed the legs for the phototaxi experiment. So why is it so different? Okay, so here I have to make a little detour. Newton mechanics, very simple. So if you want to describe this kilobot moving, well, essentially in 2D, there will be the center of mass, so 2 degrees of freedom, and because it has a backward and a front, there is also a polar orientation, and so that's why it's an active particle, and so it has also an orientation theta, and so you should write equations for both the translational degrees of freedom and the rotational one. And okay, these are just the Newton equation. There is the propulsive force, some damping, eventually external force is coming from the gravity field or the collisions. And for the angular degree of freedom, well, there is no systematic active torque because the little guy has no reason to rotate right or left systematically. They are not they are not chiral particles. There will be some damping, etc. Now, if you do this, then I will show you an experiment that I conducted with this guy, but that's essentially the same thing. And I impose the translational degrees of freedom by driving the motion along these square lines. And what you see is that at each corner, the little guy is turning in the direction that I impose. And you immediately realize that this is something these equations cannot describe, because the equation for the angular motion is completely agnostic to the translational degree of freedom. It has no knowledge of it. And the fact is that you actually need to introduce a torque, and this torque is a torque that couples the translational degrees of freedom to the rotational one. And a very simple explanation of the origin of this torque is that the center of mass and the center of application of the friction force have no reason to be at the same point on these bodies. And this will generically induce this realigning torque. How does that explain what you have seen so far? Well, this difference of location between these 2 points, well, you can have the application of the center of application of the frictional force can be actually behind or in front of the center of mass, and this will actually control the sign of this torque. So it means that for these legs, it happens that the one that has more frictions are the one at the back. And so for these legs, the sign there is positive, which means that this torque will align you on the external force field that you feel. And if you do a very simple experiment here, you will see that this one is always going down the gravity field. The other one, on the contrary, the sign is opposite. And so if you put it on this inclined plane, you can see that just because of these mechanical things, is going upwards. And so that's why this one was no falling from the twisting table. Okay, so here we have this very simple example of the fact that the detail of the design matter, and actually it can be quite crucial. So we can simulate these equations for the problem of the phototaxi. And then what we observe is this kind of result, which is, I think, quite impressive. So here what you have is the time you need to have half the population of the particles to enter in the light. And so here on the x-axis, what you have is the strength of this self-alignment. And again, it can be positive. It means you go downward the force that you feel, or it can be negative and you go upward. So remember that when the guys were arriving in the light, essentially what they were feeling was the wall that was created by the others. And so in the experiment, we were somewhere there. So actually, we were quite lucky. That's the first observation, is that we were close to this minimum here. And that's what we could see in the experiment, is that they aggregate, but eventually, on very long time, they will fill the light zone. But just imagine that we would have taken a self-alignment that would have been much larger, then they would never reach, they would never fill the light zone. Then in the experiment we had the other case. It was actually very close, and that's why there was not so much difference. And here again you can see that it fills the light zone a little bit faster than there. But then you may say, well, if this is better, then I should go more to the left. But if you go more to the left, then you hit the wall here. And this wall is because there are so much pushing against the force that they feel that they form mini cluster and they never actually move, even if the engine is running like mad. Okay, so that was just to illustrate this problem of the importance of the design, the kind of reality gap that you can face if you try just to make robots. And this is really for the simplest task. I mean, we just say the robots stop in the light. There is no intelligence, nothing. There is no gradient to compute, nothing. And still, the design of the body just matters a lot in achieving the task or not. Okay, now let's move to the second point, which is evolutionary swarm robotics. So now we want to do more. We want this population of robots to learn something. So, and to really do intelligent or smart active matter. So, the little robot, we have heard that many times during those days, is acting. That is, it's obeying some kind of physical dynamics. Here I will consider over-damped dynamics, so the physical degrees of freedom, QI, are obeying some kind of over-damped dynamics, and these are physical parameters like the propulsion speed, the motility, or whatever. Then, because it's a robot and not just an active particle, it can sense its environment, so it has sensors, and sensors are really degrees of freedom, which means they also have some kind of dynamics, and the sensor can essentially probe all the physical degrees of freedom, so all the positions of or the orientation of whatever on all the other agents. Now, if you want to do something on the basis of something that you have sensed, it's a good idea, because this is fluctuating a lot. I mean, there is noise, there are collisions, etc. So this is varying on the time scale, a microscopic time scale. So because of that, so are the sensors. And it's not a good idea to take a decision each time there is a change at that pace. So you need a memory to somehow integrate on a certain time scale this information that comes from the microscopic sensors, eventually aggregate them in some observable that gives you an idea of your behavior. Of course, this is extremely fuzzy, but that's this function g of s. That's all what you have anyhow. You integrate it over time and you store this in some memory. And that will be important because there will be already a first time scale here, and then there will be the time scale that is set by this integration scheme. Okay, and then you compute a reward based on this observation. And now you should do something with this reward. That is, you should decide something, you should think or make a decision or take a policy. And what is a policy is deciding your physical parameters on the base of your memory or your sensors. Okay, but now this function, which is a controller, that's exactly the controller of the robot, also depends on parameter, which I call the PI, or the WI if you are more like neural network oriented. Most of the talk that we heard, we were here doing some kind of learning algorithm or reinforcement learning, eventually off-board or in-board, it depends, but that was taking place there. What I propose to do is to remove this algorithm, but have a friend. That's where social learning will come in. So now I have a friend, and my friend is behaving like me. It has also all these parameters and functions. And so it means it also has some rewards. And depending on this reward, it will have to make a decision to choose a policy. And how is it going to do that? How are they going to do that? Well, they will shake hands, and they will compare their reward. And now, if this one has a larger reward than this one, for instance, then we'll say, okay, take my parameters. Probably I'm behaving better than you are. That's just the idea. It's not that I know that my score is great. Actually, alone, I have no way to know if I'm doing well or not. I just have a value for the score. But then I meet someone else, and I can see that he has a lower score. So I say, okay, do like me. And that's all. Okay. So this is the idea, and so this is what we are going to do with an experiment with 64 robots. And again, I take the simplest case. Two dynamics are pre-programmed inside each robot, D0 and D1. The controller is just input light sensor, and output is the selection of D0 or D1. So you see here the controller is essentially a perceptron. It's just one entrance, one output. I mean, you cannot make simpler than that. And the first thing that you can do is, okay, you know what is the good value for, so essentially what you have to decide is the threshold. So the threshold will be random initially amongst the population, but before doing this, what you can do is, well, as an experimentalist, you can set the threshold. You know, if you put the threshold there, you are good. So this will give you a reference curve, and this is the number of guys that are stopped in the light, and this is the number of guys that are moving in the dark. And so you see that progressively you fill the light zone. Okay, but this is because you knew the threshold. Now they have to find the threshold. So they have to learn it, and the reward will be the light seen in a certain past time window, let's say in the past 10 minutes. So the little guys are moving around. They have random thresholds, so you can imagine some, they believe that there is plenty of light everywhere, and so they stop in the dark because they are happy guys. And then you have those who go in the light, and the sensor tells them, no, but you are in the dark. These are the permanently unhappy guys, and they run like mad everywhere. Okay? Then you may be lucky enough that some are a little bit cleverer than that, and indeed they stop in the light because the sensor is at the right value. And these guys will meet. Eventually, the one that stops in the light because he's having the right threshold will communicate his policy. The policy here is just one scalar of the threshold, so very simple, and the population will learn. And indeed, it works. It's not as good as the preset, of course, because preset is the ideal case, But here we have 4 experiments, and we see that in each case, the population learns, and eventually the population ends up in the light. Okay. Yes?
With friend, you mean anybody you meet?
Sorry?
With a friend?
Yes.
You mean anybody?
No, so with a friend, what I mean by a friend is someone you can communicate to. So here, the communication, we have to set a communication range. So you can do different things. You can say broadcasting to all the room here, and then pick up randomly someone and say, you have a good score, give me your parameters. Or you can say, no, I will do nearest neighbor or some communication range. And this is what we do here, and this is where it's the most interesting because it means that your learning abilities depend on the geometry in the real space of where you are. And so you can have people who are completely isolated, stop because they believe there is light, but they are stopped alone in the dark, and they have to wait for someone to rescue them because they will not move.
How do they communicate?
So they have small infrared communication channel, and you can set the range. So typically it's body lengths or 2 body lengths. So they learn. So that's nice. I mean, there are not so many experiments with 64 robots that demonstrate learning in this kind of collective learning behavior. Okay, now that was very, very easy. You just had to find one number on an axis, and as a matter of fact, there are plenty of value of the threshold that are good, provided that you are being the low light value and the high light value. Any values there is good. So you have actually many solutions. So the exploration space is not that large. So let's do something a little bit more complicated now. We don't pre-program any dynamics, which means that the controller, again, input is the light sensor, but the output will be the power of engine 1 and engine 2. I told you that there are 2 little engine, 2 little vibrator, and so the output is really the value of this. So it's not anymore I move, I don't move. Some will start spinning, all possible dynamics will emerge, and now we have to decide what is the shape of the controller. And the shape of the controller will be essentially a 2 plateau, like an arctangent, an hyperbolic tangent curve. And so each of these curves will have 4 parameters. The value of the first plateau, so I should say what is this? This is the strength of the power of the engine as a function of the light intensity. So what you would expect is that they adopt this orange curve, that they should slow down in the light, accelerate in the dark for a value that is at the right place, so a good threshold. But all these possible curves exist. That is, they could even take a wrong decision, that is to stop in the dark and to accelerate in the light. And initially, so now it means that each of these curves have 4 parameters, the value of the plateau here, the value of the plateau here, the position of this, and the slope of this. And they have 2 motors, so you have now an 8-dimensional parameter space, many more possible behavior, and it's not clear that this poor 64 robot will be able to find a solution in this parameter space. But it actually works in less than 2 hours. Anyhow, after that, the batteries are off. And indeed, they learn. So here again, you have 4 experiments. So here, this is with rather high contrast. Of course, if you put a high contrast, it's easier. And also, initially, they are uniformly positioned. And then we vary a little bit this. So here you have a high contrast, but there is none of them in the light at the beginning. And as you can see, it makes the task a bit harder. And then when the contrast is low, well, then they really have a hard time to learn, and they don't really learn. Okay, but so this is a demonstration that a bunch of 64 extremely elementary robots, no deep neural net, I mean basic controller, just a 4-parameter function, can learn collectively this simple task. Okay, can we model that if we want to go a little bit further and get some kind of theoretical description of that? So active matter, this we know. We have our favorite model of active matter. This is the one with this self-alignment because we know that these robots have this property, but otherwise it could be ABP, WAP, or whatever you want. Then you need a controller. A controller is a function that will fix the values of these parameters that you have in this equation. Here there is only essentially one, which is the active force, but there could be many. And this will be a function of something measured in the environment where the robot is, And this will be a function with parameters. That's exactly the example of function I gave here. Now, what about the learning? Well, the learning, you can actually say, okay, let's also do Langevin dynamics. We like Langevin dynamics. So let's say that the weights are obeying this Langevin equation. So what is it? Well, first, we confine the weight in some kind of potential because we don't want weights to get crazy values. This is the equivalent of regularization in neural nets. Then there is this exchange term, and this exchange term just say, well, if the score of j is larger than the score of I, if I'm in the range of communication, then I will exponentially, my weight will exponentially converge to the one of the guy who has a higher score. It's very far from the real way they communicate. It's really a physicist-like description. And we also, and we also add some, we can add some diffusion in the score space, which is something that is important. It's called mutation when you do a genotypic genotypes evolution. And the score here, well, the score is very simple. It's just the light I've seen integrated over a time scale 1 over alpha q. And the score is also exchanged when they meet. And this is because if they exchange the policy, well, you want them to have the same score or the same reward. So they could learn it, and you could protect them the time they need to learn it, but it's more efficient to transfer it. Okay, then when you do that, you can simulate this. And it's amazingly well, it's working amazingly well. So this is, again, you simulate them, again, for the same phototactic task with the same number of agents, the same ratio of the size of light with respect to the total size of the arena. And, well, you describe with this simple set of equations, which I insist is pretty far from the real communication channels and so forth and so on. And you describe the data. So here, again, this is the one that stop in the light, this is the one that move in the dark, and this is the one that are doing bad. So this is the one that are moving in the light, and this is the one that would stop in the dark. And the 4 features are rather well captured by these simple equations. That's a good starting point, because we know how to deal with these kind of equations. Okay, so can we try from there to derive some kind of effective hydrodynamics theory for not 64 robots, but if we want someday to move to 10,000. So the idea is, because the system is rather dilute, is to get inspiration from the Boltzmann equation formalism, where you exchange momentum. We all know this. And the idea is just, well, okay, you exchange momentum, you can exchange orientation if these are aligning particles. This has been done. I mean, kinetic theory for particles, for granular matter, for active matter, this has been done successively. And what we just propose is to add, okay, let's also exchange policy. When there is a collision, now there is one more vector to exchange, which is the policy. It's an asymmetric exchange because it's reward dependent. But, I mean, that's not so bad. And so you can say, okay, the one particle density for the policy, the memory, the internal state, so essentially the sensors of the robot, the position and time, will obey some Boltzmann-like equation. This is essentially the advection and diffusive transport. There will be some collision, your favorite collision terms. Choose the one you like. And then you have to say something about the memory and the policy. The memory was very simple. The memory is just an integrator. So it's a deterministic equation. And so the Fokker-Planck associated to this deterministic dynamics is just this. This is the way this distribution will change the value for the memory. And for the policy, so the policy, I told you we can put some diffusion, some noise in the policy space, so that would just be diffusion for the distribution. But there is this teaching part, when I decide to give my policy to the others, and this you can describe just by a master equation. So you have to specify the rates with which a little robot with a memory M and a policy P will end up with a memory M prime and a policy P prime during the collision. And these rates, essentially, they will be a function of the difference between the two scores, and that's it. And that there is not much more than that. Then you have to crank up the manivelle. And when you do so, oh yes, just a remark. For simplicity, everything is localized in space, so there won't be any gradient terms in this policy and memory, but in principle they could be. Okay, so of course you get mass conservation. That's the number of robots doesn't change in time. But of course you have here fields that are this velocity, average velocity field and average diffusion fields, which are the integrated over all the degrees of freedom, and you have to write equations for those. So I will not spend too much time on that, but the mass is the only thing that is really conserved in here. So this one we know it's a slow mode. Now the other modes are faster if there is no phase transition going on. If there is alignment, you could have slow modes associated to the broken rotational symmetry. That depends. That will depend on the case you are considering. But anyhow, you will find, and this is where it becomes interesting, all the complicated Toner 2 or Navier-Stokes, whatever terms for the velocity and the diffusion here. And then you have terms that are specific to the problem we are considering. And there are terms, and these terms, they essentially contain the diffusion in the policy space, but also correlators that correlates your reward with your behavior. And that's good, because that's exactly what we want to capture, is how your behavior and your rewards are correlated. I mean, not even talking about causality. Okay. Then you need to describe these rewards, and these rewards are a function of the memory. They are simple function of the memory in principle, but so it means you have to describe the memory field and the reward field and so forth and so on. And again, here we can see immediately the importance of this concept of time scale that we have not really discussed much during these days, but that is crucial. Somehow you have a fast dynamics, then you integrate it to make sense out of it, and then on even longer term, you decide to adapt your dynamics on the base of some learning process. But so there is a separation of time scale between these terms, these ones, which are the memory one with the memory rate, and these ones, which is essentially the exchange rate. That depends, as you can see, it comes with density. Okay. And finally, you get the equation for the policy field. And good enough, you can again see that the policy field is directly governed by the correlation between the reward and the way you behave. That is your policy. Okay, etc. And then, of course, you need closures, etc., etc. Now, what can we say already at this level? So if you take the simplest case where you have an homogeneous system, that is no gradient of density, something very simple, so not at all the light, the phototaxi that I presented, which immediately will create gradients of density, of course. But you just take a well-mixed system of agents. The equation actually already contained a few interesting points. First, you immediately see that the policy evolves proportionally to the variance of the policy. And that's nothing but Fisher's fundamental law of evolution. You cannot evolve your policy if there is no diversity. It just comes out naturally from this hydrodynamics equation. Now, the diversity itself is pushed by the mutations, by the noise in the policy space, and otherwise converges rather rapidly to zero. So you need mutation if you want to sustain diversity. Okay, we tested that in a number of settings. I will not enter into the detail of this simulation, but this is a system of basic agents that have to learn some simple task. And we can see that the policy starts here from, okay, around a number on average, which is 100. This is completely arbitrary, and converge to some value that was the goal. And this is the fluctuation of the policy, and we can say that indeed it decays. It decays actually as 1 over t if there is no mutation, and it saturates to a finite value if you add mutation to the dynamics as prescribed by these equations. What I find interesting is that there is a characteristic rate in this behavior that you can extract. And this characteristic rate, I mean, with no surprise, there is the exchange rates times the density. And that's just because you have to communicate so something happens. But then here, this is somehow how much, remember this G is this observable that you build with your sensors. It's your estimated behavior. And your estimated behavior, your estimated behavior must be maximally sensitive to your change of policy. And this is fair indeed. If when you change your policy, the behavior does not change, what are you going to learn? You should not be in a flat space in terms of this response. So this characteristic rate emerges, and it's actually governing the learning rate, which is a balance between this rate and the mutation one, and of course the policy uncertainty, which is where it also enters into account. Okay, so that I think a general learning principle that we learn from these equations. Okay, how much time do I have? Not much. So let me just puzzle you so that we can discuss at the coffee break. I think that's a good way to finish. So since I have equations where I can simulate also these systems, I will take a very, very simple case. I will take active Brownian particles with a velocity and a diffusion, and I will take something that I actually use to try to debug the code. So a stupid controller. So let me clarify. The controller is measuring the light, but then the velocity that it chooses as a function of the light that it measures is independent of the light. So it's a stupid controller to perform phototaxi, right? It will set a number. I mean, this is a decent function, but so the class of function the controller has access to are only the constant function, the one that are agnostic to light. So for a single robot, it's really stupid because whatever the velocity that you point, you are just rescaling the time, so it's completely degenerate. It's a degenerated agnostic to light controller. You cannot make something more stupid than that. But the same, you still use the same social learning rules. That is, the little guy, they walk around, some are in the light, they're happy, they get suntanned because they went to the south of France, and some others, they spend the time in Seeon, and they don't have as much sun, and they still exchange their rewards. But I mean, for what purpose? Since all the rewards, all the policy are equivalent. Yet, if you put them in a box with a gradient of light, they accumulate in the light. Let's go for the coffee break.